Welcome to this video lecture. This is Mark Scythian, FAA licensed aerospace technician, airframe, power plant, and avionics certified. The date today is February 26, 2017. The title of this video lecture is 2008 Chevrolet Corvette Top Speed Calculation. This lecture will cover the maximum possible road speed of the 2008 Chevrolet Corvette with the C6 body based on the specifications of this given vehicle. The forces opposing an automobile in motion at cruise speed when at zero acceleration on level, paved, and dry road are aerodynamic drag and tire rolling resistance. Aside from transmission, driveline, and engine control module ECM limitations, the only other limitations regarding maximum automobile speed when on level, paved, and dry road is the maximum available brake horsepower loss to overcome aerodynamic drag and tire rolling resistance. When the maximum available brake horsepower is entirely lost to aerodynamic drag and tire rolling resistance at a given speed on level, paved, and dry road, the given automobile will reach its top speed. The 2008 Chevrolet Corvette specifications are as follows. The 4-stroke gasoline piston engine is a 6.2 liter V-8 LS3 crate engine with a displacement of 6,162 cubic centimeters, cc's, a bore and stroke of 103.25 millimeters by 92 millimeters. There's 25.4 millimeters to 1 inch, so that translates to a bore of 4.065 inches and a stroke of 3.622 inches. The maximum torque output is 424 foot-pounds at 4,600 RPM. Automobile weight 3,272 pounds. Coefficient of aerodynamic drag 0.286. Projected frontal area 22.3 square feet. The elevation above mean sea level operating condition will be 925 feet above mean sea level in an air temperature of 59 degrees Fahrenheit, 0 mile per hour headwinds, and the road conditions are level, paved, and dry. So the first thing we have to do is calculate the maximum available piston engine brake horsepower, and the foot-pounds torque at given RPM is directly proportional to the brake horsepower, or the usable horsepower available at the crankshaft after factoring out all friction horsepower losses. So we would start first with the brake horsepower formula for piston engine, which is the brake mean effective pressure in PSI times the piston stroke length in feet, L, times the bore cross-sectional area in square inches, A, times the number of power strokes per minute, N, times the number of cylinders, K, divided by 33,000 foot-pounds per minute, which is the number of foot-pounds per minute to 1 horsepower. We must use foot-pounds per minute because we're dealing with revolutions per minute, not revolutions per second. BMEP, brake mean effective pressure, that's the pressure exerted on the piston during each power stroke. And in a 4-stroke piston engine, there's exactly 2 revolutions of the crankshaft for every power stroke. So the power strokes per minute will be equal to 1/2 the RPM. So the brake mean effective pressure in a 4-stroke piston engine is equal to 150.8 times the foot-pounds torque divided by the cubic inch displacement of the entire engine. 1 cubic inch, or CI, is equal to 16.387 cubic centimeters, or cc's. So to calculate the CID, we would take 6,162 cc's and divide it by 16.387. So that translates to 376 cubic inches total engine displacement, which is also equal to 6.2 liters. 6.162 liters to be exact. 1,000 cc's to 1 liter. So we calculate the brake mean effective pressure for the 4-stroke piston engine. In this case, it's 150.8 times the maximum torque output of 424 foot-pounds divided into a total cubic inch displacement of 376 cubic inches. So during each power stroke at maximum torque output, there will be 170 pounds per square inch of brake mean effective pressure during each power stroke. Next, we have to calculate the piston stroke length in feet. So we take 3.622 inches piston stroke and divide it by 12. That would be 0.3 feet piston stroke to represent L. The A is represented by the bore cross-sectional area. which is equal to the bore diameter, 4.065 divided by 2 to obtain radius, then squared, then times pi. So the bore cross-sectional area, A, is equal to 12.97 square inches. The number of power strokes per minute, N, is equal to the RPM divided by 2 in a 4-stroke piston engine. So since we're operating at maximum torque output, which is directly proportional to brake horsepower, we take 4,600 RPM, the RPM in which maximum torque is reached, divide that by 2. So the N is equal to 2,300 power strokes per minute. K is the number of cylinders, in this case 8 cylinders, V8. So the maximum brake horsepower at 4,600 RPM is equal to 170 psi brake mean effective pressure times a piston stroke length of 0.3 feet times a bore cross-sectional area of 12.97 square inches times 2,300 power strokes per minute times 8 cylinders, that quantity divided into 33,000 foot-pounds per minute. So the maximum available brake horsepower at 4,600 RPM is equal to 369 brake horsepower at 4,600 RPM. Next, we use the elevation above mean sea level value of 925 feet above mean sea level. We then enter that into the atmospheric pressure formula between mean sea level and 36,089 feet above mean sea level. We take the 925 feet above mean sea level, divide it by this value here, then this quantity subtracted from 1, and then this entire quantity taken to the 5.255876 exponential power. That whole value then multiplied times 14.7. So at 925 feet above mean sea level, the atmospheric pressure will be 14.21 pounds per square inch. Next, we use that information to calculate the air density in slugs per cubic foot, which would be equal to 29 times the atmospheric pressure, 14.21 psi, times 0.031, which is the number of slugs to 1 pound, 0.031. That quantity then divided into the ideal gas law constant for air, 10.73, times the absolute air temperature in Rankine's degrees of the air, which would be equal to Fahrenheit air temperature plus 460. This entire value then equals 0.00229 slugs per cubic foot air density when at an elevation of 925 feet above mean sea level and 59 degree Fahrenheit air temperature. Next, we have to access the formula to calculate the watts and power required to overcome aerodynamic drag, and that is equal to the aerodynamic drag coefficient times rho, which is the slugs per cubic foot air density, times the projected frontal area A of the vehicle, times the feet per second speed of the vehicle, assuming no headwind, so that's the airspeed, in feet per second cubed. This quantity then divided by 2. Next, we access the power in foot-pounds per second to overcome tire rolling resistance. That would be equal to the automobile weight in pounds, W, times the automobile speed in feet per second, V, times the coefficient of tire rolling resistance. And in this case, an automobile or light truck below 8,000 pounds weight rolling on level, paved, and dry road is equal to 0.012. So when we multiply all that out, we will get the foot-pounds per second required to overcome tire rolling resistance. To calculate the top speed of this given automobile, the total horsepower lost to overcome both aerodynamic drag and tire rolling resistance will equal the maximum available brake horsepower of this given automobile's piston engine. 1 horsepower is equal to 550 foot-pounds per second of mechanical power, which is also equal to 746 watts. So if we set this equation up to figure out what the top speed is, that would be equal to the power required to overcome aerodynamic drag plus the power to overcome tire rolling resistance equal to the maximum available brake horsepower. So we take the known values and we just simply enter them into that established formula. So we know everything but V. Next, we compute what we do know. So when we multiply the knowns, we get the first equation line here. And then as we simplify the double dividends here, we can get the reciprocal of the last dividend as dividing the first value into the other. When we simplify it down, we're left with this neat and clean equation here, which when we solve for V, will calculate the automobile's top speed in feet per second. So starting at this point now, this equation, when we solve for V, we will calculate the top speed of this given automobile in feet per second. So there are three ways to solve for this equation. If you're really good at factoring polynomial equations longhand, then you'll probably eat this equation right up quickly. And the second option is to input an approximate top speed intuitively to automobile. So automobile like this, the 2008 Chevrolet Corvette with the LS3 crate engine, probably equal at least 220 miles per hour, if not more. Just an intuitive estimation. So let's say using 2 and 3, choices 2 and 3 are the fastest method. So let's start with choice 2. Statistically, most people would want to use 2 or 3, and some people are really fast at longhand polynomial factoring, even with negative square roots and imaginary complex numbers. But we'll just assume most will choose 2 or 3. So we'll start with choice 2. Since this is a 2008 Chevrolet Corvette with a C6 body with a maximum brake horsepower of 369 brake horsepower at 4,600 RPM and driving on level, paved, and dry road, it is not unreasonable for this automobile to at least reach a top speed of 220 miles per hour. Let's find out if this is true and make adjustments and calculations to accuracy. I call it adjustment calculations to accuracy. So miles per hour to feet per second is equal to miles per hour times the ratio of 22/15. There are 22 feet per second to every 15 miles per hour. So we convert the 220 mile per hour estimation to feet per second. So 322.7 feet per second is our first estimation value. All we have to do is enter that in, substitute that in for V. We have two different V's, but they're both feet per second equations to each other. So we can solve for both V values in these separate equations because the units are identical. So when we do so, 322.7 cubed times this constant divided by this dividend added in the same value here, we get 351.8. So we're a little low. We need to reach 369. So we'll try again. We'll go up a little higher from 322.7 feet per second. Let's try 325. Same process, we just enter them in by substitution. So we have to reach 369, so it's still a little low, so we'll try again. 368, very close, pretty much the right answer. We'll go up by 1/10 of a foot per second, 0.1. And when we do so, we get a perfect match, equals 369. So 369 to 369 is 0. This is where at 328.1 feet per second, this is where this given automobile will reach its top speed. So then we can convert the feet per second into miles per hour. In this case, it's 15/20 seconds times the feet per second to get miles per hour. So in this case, it's 223.7. We rounded up to 224. So the top speed of this given automobile is 224 miles per hour. And if you need that in kilometers per hour, that's 224 times 1.6. 1.6 kilometers to 1 mile. So 358.4 kilometers per hour, or 224 miles per hour is the top speed of the 2008 Chevrolet Corvette. So the final answer here is the 2008 Chevrolet Corvette with a C6 body powered by the GM 6.2 liter V8 LS3 crate gasoline 4-stroke piston engine, and when driving on level, paved, and dry road will reach a top speed of 224 miles per hour while at its maximum available brake horsepower of 369 brake horsepower at 4,600 RPM. Now method 3, we can go over to the iOS Android screen recorder now. Then there's method number 3. You can either use a standard graphing calculator, or if you go to the Google Play Store and you download the Math Lab apps, you can actually have an automation problem solving in real time. You do need an internet connection. So if you click on the calc function here, you can just go ahead and enter that equation, which when solving for V establishes the top speed. we can substitute using x for v. So 0.0146 x cubed representing v cubed divided by 1492 close parentheses plus 3926 x representing v divided by 550 close parentheses equals 369 maximum available brake horsepower, enter, and then it will actually solve the polynomial equation longhand in an automated sense with the internet interface. So there's a lot of imaginary roots as in negative square roots in the equation, so you have to use the integer, no imaginary roots and no negative values. So 328.0865, 328.1 feet per second. So this is like the fastest way to solve it if you use the MathLab app. So after entering in that equation through the MathLab app on Android, iOS, or on a graphing calculator, you can quickly calculate what the V component is, and in this case, of course, we matched 328.1 feet per second as the maximum velocity, and then when entered into that equation down here, we calculate that the total is equal to 369 brake horsepower required to overcome both tire rolling resistance and aerodynamic drag. So 369 minus 369 equals 0, so that mathematically proves the top speed of this given automobile is 328.1 feet per second, or 224 miles per hour. And that's on the assumption that there are no lockouts on the electronic control module, transmission, and drivetrain to maintain street legality. But assuming that's not occurring and it's strictly overcoming aerodynamic drag and tire rolling resistance, the 2008 Chevrolet Corvette, the C6 body, powered by the GM 6.2 liter V-8 LS3 crate 4-stroke gasoline piston engine when driving on level paved and dry road, will reach a top speed of 224 miles per hour while at its maximum available brake horsepower of 369 brake horsepower at 4,600 RPM. Thanks for watching this video and have a great day.